Hey everyone, we are looking at three different types of difference quotients and also why they matter. So first, the types. Two of them you've seen before, one you haven't. So a forward difference quotient, basically, so say I want to know my slope at x. And I can estimate my slope at x if I go to the right, say 0.1 or however far, some number, some distance h. I think they use h because of horizontal, makes sense. And we have some change in y, our delta y. So our slope from x to x plus h is going to be delta y divided by h, just that little slope there. Our second one, and this seems like a weird thing to do, but maybe it's just the information you have, but we could, instead of going forward some distance h, we could go backwards some distance h. But again, our slope between x and h away from x, even if we went backwards, is delta y, the change in y, divided by our h. The third way is called a symmetric difference quotient, and this is what we actually used when we were working with tables. So you've kind of seen this before. So you have backwards a distance and forwards a distance, and then you have that change in y, and the slope there is going to be a bigger delta y, but it's divided by 2 times our h. And that's called a symmetric difference quotient. And we need to know about these three different things for a couple reasons. One is to know about accuracy a little bit, and you might guess that going to each side is actually more accurate. So why wouldn't you do that in the first place? Well, maybe just because of the fact that it's easier to just go, say, from x equals 3 to x equals 3.1 rather than having to go back and forth. But we used this on tables and it worked really well for us. So our calculators are programmed to do some derivatives, and the way they are programmed is this symmetric difference quotient. We're going to see that in a later video. Okay, so now using an example of just how these three difference quotients work when we're looking at forwards, backwards, and symmetric. Say we want to estimate our slope at x equals 3 for the function f of x equals x to the 4th. So to do a forwards difference quotient, if we're using an h of 0.1, we're doing f of 3.1 minus f of 3 divided by 3.1 minus 3. So looking at that as a shortcut, you're on the denominator, there's your h, the 0.1. If you throw that guy into your calculator, you get an approximation of 113.521. X to the 4th gets really steep really fast, so we have a slope of 113 and change. If we did a backwards difference quotient, we're going from 3 back to 2.9, so we're talking about f of 3 minus f of 2.9 divided by 3 minus 2.9. There's that 0.1 again, our h. And if you chuck that in your calculator, you will get 102.719. We can make this more accurate though. Not that you can tell so far how accurate either of those are. But if we go with a symmetric difference quotient, so we have f of 3.1 minus f of 3, f of 2.9, we're going symmetric, and we divide that by 3.1 minus 2.9. You have a bigger change in y, but you're dividing it by twice as far, the 2 times our h, the 0.2. If you throw that in your calculator, you get 108.12. Now, I know you don't have a way of knowing this just yet, at least not very easily, but the actual value of f prime of 3 is 108 exactly. So which is the most accurate? Well, clearly it's the 108.12, that symmetric difference quotient. So our calculators are programmed to do this too, and you're going to learn about that next. But here are your three difference quotients: forwards, backwards, symmetric. Forward gets used because it's convenient, but symmetric's typically a little more accurate, as you can see here.